Hello, this is Bruce Capron. It is February the 25th, 2016, and this is a recording of an interview that I had with Professor Steve Cook at the University of Toronto, where Steve is university professor in the computer science and mathematics departments. This is part of the ACM Turing Award Winners Project. Professor Cook received the ACM Turing Award in 1982 in recognition for his contributions to the theory of computational complexity, and in particular, the theory of NP-completeness, which he introduced in his 1971 paper, The Complexity of Theorem Proving Procedures. And so now what you'll be seeing is my interview with him. Oh, Steve, you were born.
Hello.
You were born and you grew up not far from Toronto in Western New York. As a child, did you already have an interest in science or mathematics?
Yeah, well, I certainly had an interest in science. My father was a chemist and worked for Union Carbide, a branch, and so I was interested in science. And I was good in mathematics, but I didn't think in high school that was going to be my chief interest, but the big influence on me when I was in high school was Wilson Greatbatch, who was a resident of Clarence, New York, where the same as me, and he was an electrical engineer, but a very creative one, and transistors were a very new thing then, and he designed a transistor circuit that went boop, 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 and eventually turned it into a artificial pacemaker for hearts, which was implantable, and that had never been done before. Well, of course, you couldn't do it with vacuum tubes, obviously. And so he eventually got the ushered into the Inventors Hall of Fame in the United States for inventing this thing. But while he was doing this, and I was in high school, I helped him out. He had a little shop in the top of his garage in which he worked, and he would draw pictures of transistorized circuits, and I would solder them together, and then he tried them out, and I could see on the oscilloscope this bip, bip, bip.
So this was in the late 1950s?
That's right. That's right, because I was in high school, and I graduated from high school about 1957, and I don't think it actually got turned into a pacemaker till some years after that. Also, he worked for an electronic firm, and he got me summer jobs there. So I was very interested in electronics, and I thought that was going to be my profession.
And so you mentioned your father, and your mother was also a teacher?
Yeah, well, she had two master's degrees. The father and mother met at University of Michigan, and she got a master's degree in English, in history then, I guess, yeah. And of course, where my father got his PhD in chemistry. And then later on, when I have three brothers, and she was mostly taking care of us, but when we were all going off to various places, then she was a teacher. She got a second master's degree in English, and then she was teaching at a community college in the area.
So you mentioned that you had quite an early introduction to, I guess at the time was very high technology electronics. What was your first exposure to computers and computer programming?
Yes. Even in high school, I had a good math teacher who was somewhat interested in computers, and he took us to downtown Buffalo to some meetings, so I already had some idea about computers. But it really wasn't until I went to University of Michigan, which was my undergraduate school, since both my parents were alumni, that there seemed to be no choice. And so my very first year, which would have been, I guess, the 58, the spring term, I took a course, a 1-hour course in programming. And this was from Bernard Galler. And so we learned how to program, and I think it was the IBM 650, which was a vacuum tube machine whose memory was on a drum, just to put you in the category of what computers were like then. So that was probably my first real access to computers, but I enjoyed it a lot, and I started writing fun programs. Like, I remember early on, I wrote a program to test Goldbach's conjecture, which was that every even integer is the sum of 2 primes. So I tested it up to some large number, and it turned out to be verified.
And at Michigan, you started off in electrical engineering?
That's right. I actually started, it's engineering science, I think, but I thought I was thinking in terms of electrical engineering, but my very first year, I took a calculus course from Nicholas Kazarinoff, and it was, I guess, a slightly, not just the completely typical calculus course, slightly more advanced. And anyway, I got quite interested in the course, and Kazarinoff got interested in me, and he would give me special homework theorems to work on. And in fact, he was so impressed that he said I could skip the second-year calculus course, which I kind of regret now because I never learned two-variable calculus, but and go on. There was a third-year course, and also then I took a third-year course in linear algebra. So yeah, I got off to a good start in mathematics.
And eventually you switched into?
That's right. After, I think it took 2.5 years, and then I finally switched out of engineering and became an official math major. That's right.
And so you were successful enough then that you ended up going to Harvard?
Yes, indeed. Yeah. That I was quite excited about that. I must have gotten good reference letters. And so, yes, I guess it would have been 61. I became a student for a master's degree in the math department, and so I got that in 62, and then I needed a thesis advisor, but I'd taken a logic course from Hao Wang, and he was not in the math department. He was in the division of applied physics, but I mean, certainly interested. He was really a logician. Logic was his major interest, but he also was interested in computers. And before coming to Harvard, he worked, I guess, for both Bell Telephone Labs and, excuse me, the IBM Watson Research Laboratory in Yorktown Heights, New York. And there, he wrote a program to prove theorems in the propositional calculus automatically. That was one of his interests, trying to make automatic theorem provers. And it apparently was very successful because he used an IBM 704, which is another vacuum tube machine. And in just 3 minutes, it proved all the 100 or so propositional tautologies in Russell and Whitehead's Principia Mathematica. And that was a big deal because other people, Newell, Shaw, and Simon, had tried to make automatic theorem provers for propositional calculus, and apparently they weren't very successful.
So Professor Wang was also very interested in foundational issues in mathematics and logic and computability. And I'm wondering, it seems that both with the automated theorem proving and with his interest in computability, that really had a big influence on the work that you've a lot of the work that you've done.
That's right. I mean, it certainly did. There was no question about that. That yeah, he was interested in the Entscheidungs problem of Hilbert, which is the problem of determining whether a given predicate calculus formula is satisfiable or not. And and then it was, of course, that Turing and others proved it's unsatisfiable. So then how simple a formula, class of formulas can you make to make it still unsatisfiable? And there was the so-called AEA case, for all there exists for all case, and then proved it was still unsatisfiable. So he was part of that. And yes, that did have an influence on me later on.
But computational complexity has always been a theme in your work, and I'm wondering if you can say a little bit more about what your PhD research is based on.
Yeah. Okay. So my so some background for that. Computational complexity was a new subject, of course, and this was in the early 1960s. In '63, I think it was, Hart, Madison, Stearns published their famous paper in which they introduced the word computational complexity on the computational complexity of functions or something like that. And so Hart Manis came to Harvard and gave a talk, and so I became quite interested in that. And then the other influence was by Alan Cobham. Alan Cobham had a degree from Harvard, and he was a graduate student there, and he wrote a thesis, but he never got his PhD because the math department requires, in addition to a thesis, it requires a minor thesis. And Alan never bothered with the minor thesis, but he went off to work for, again, IBM Watson Research Lab, and he was connected with, he was a friend of Hao Wang, and he would come, and so I got to know him. And his famous paper was on the intrinsic difficulty of intrinsic computational difficulty of functions. That was his paper he wrote, and he was interested in. I think this is really before Hart, Manis, Stearns. That happened. But he was interested in what sense are some computational problems harder than others, and he compared multiplication, addition as example. What way is multiplication harder than addition? But his result, which I mean, one thing he did that really had an influence was he introduced the notion of polynomial time, what we would now call polynomial time computable functions. And he argued that this is an interesting class, a complexity class, because it seems to be all feasible functions. And if you're not polynomial time computable, you're not going to be feasible. He made that argument. And then he also came up with an interesting characterization of the polynomial time computable functions, namely a function is polynomial time computable if and only if it can be obtained from certain initial functions and applying the operations of composition and limited recursion on notation, and that's something he made up. A new kind of recursion. I mean, primitive recursion, of course, had been well known for many years, but to characterize the polytime computable functions, you needed this other notion, limited recursion on notation. And so that also had an influence. I was very interested in that.
But in your PhD, you considered the question of the difficulty of multiplication.
That is correct, yes. Maybe that was because of Alan Cobham's question. Yes, of course, so it's very hard to prove lower bounds. We all know that now, and that was certainly true then. So the only way to get a lower bound on multiplication was to look at the case where the inputs are only read. What do you call that? So the inputs are restricted so that you have for after each digit is given, you have to give the output for the multiplication. So online, I'm just thinking online. Sorry for the, yeah. So this was an online model of a Turing machine, which you think of an unlimited number of digits. You're multiplying two numbers in decimal or binary, whatever, doesn't matter. And so the first n string of n digits would be the n least significant digits in the two numbers, and that's enough information to get their product. And so you had to output their product, and then go on for the next two digits, and then keep outputting the product, and so on. So that was the online model. So in that model, I was able to get a lower bound of n log n over, just in log n. What was it? I can't remember exactly. Yeah, n log n over log n, I think it was. Yeah. So that was a non-trivial lower bound. That was part of my thesis. The other parts again were talked about computational, number theoretic, or real function problems.
So after graduating, you became a faculty member in the math department at University of California?
That's
Berkeley.
right.
And what year was that?
So that was 1966. Yeah. So I finished my PhD in 1966. I had been offered a job. Now the job was half mathematics in the math department and half in the it wasn't a computer science department, although they did have a budding computer science department just starting. It was a research job in the computer center or something like that. So it was only half in mathematics. So yes, so I started that out in the fall of 1966.
And so you were in Berkeley in the late 60s, which must have been an interesting time intellectually and culturally as well.
Indeed, of course, yeah. This definitely was, the free speech movement was in full form, and there were crowds of people there, and so in some cases the police were called in. There was tear gas and all kinds of stuff. Yes, all that was going on in the 60s. Yes.
So as soon as you got there, I assume, or even as you say, working on your PhD, you were already thinking of a lot of questions about computational complexity and even thinking about polynomial time. So
yes. Well, of course, yeah, the polynomial time definitely came from Cobham, so I was interested in that. And early on, I did circulate a mimeographed set of notes on something like classes of primitive recursive functions. And there were complexity classes of primitive recursive functions. And so there was work at Princeton at the time. There was a logician at Princeton, and I had read parts of Bennett's thesis, yeah, and he was anyway. His thesis was called On Spectra, which was actually a predicate calculus sign, but it had complexity theory. A lot of complexity theory results based on logic. So there was kind of two different classes of people then. I mean, these were the logicians doing complexity theory. And so he didn't talk about Turing machines ever that I remember. But I remember, so one of the complexity classes he talked about were the extended positive rudimentary relations, the classic extended positive rudimentary relations, which had some fancy definition, logical definition, and then I eventually realized, you know what this is? This is non-deterministic polynomial time. The same characterization. And so that's probably the first time I became interested in what we now call NP.
And what year was that?
That would have been, well, this 67, because I circulated this stuff, and it has a date on it, 1967. So.
And so then you were already aware of the question of what the relationship between would be between P and P.
Well, absolutely. I even put a note in there that, oh, this is interesting. So one assumes that there are problems in non-deterministic polytime that can't be done in deterministic polynomial time, but might be rather hard to prove that. And I turned out to be right on that point.
And while you were at Berkeley, you were already doing work which you ended up ended up at the ACM Symposium on Theory of Computing. Right?
Yeah, that's right. I had a couple of ACM stock conference papers. So one of them was this characterization, another characterization of polynomial time, which I think is quite intriguing. And so problem can be solved in deterministic polynomial time if and only if it can be solved by a so-called auxiliary log space pushdown machine. So what is this? That's a Turing machine that has read-write input tape, and it has a work tape, but it can only use log space, order log space symbols on its work tape and do the work. But then it's, so that model is a characterization of what we call log space, which is, as far as we know, a proper subset of polynomial time. Of course, we can't prove that either, but we assume log space is certainly a subset of polynomial time, but we assume it's a proper subset. But if you add the pushdown stack, I proved you exactly get polynomial time. And not only that, the non-deterministic version also gave you deterministic polynomial time. So I thought that was kind of a neat result. That got published in the ACM journal.
And so you left Berkeley and you came to University of Toronto in 1970.
Yes.
Were you recruited by people at Toronto?
So the story there is that the math department denied me tenure, and that's so, because otherwise I would have stayed, certainly, especially since I just married my wife, Linda, who was raised in Berkeley, the center of the universe, and she had no desire to leave Berkeley. And so this was quite, I should say, to be fair, when I proposed to her, I told her I might not get tenure. So she was forewarned. In any case, so it looked like I had to get a job somewhere else, and so I applied at other places, including Yale and University of Washington, and I think IBM Research. And then I went on a trip, but the Toronto connection, I didn't have any sense of going to Toronto, even though I have to say that I had been, no problem with Canada, because we lived in Buffalo. We used to go to resorts and summer resorts in Ontario, so that's fine. But anyway, I didn't think of Toronto, but in fact, I was recruited. Somebody in the computer science department at Berkeley, who had just come from, who had been at U of T. He was Canadian, but he was recruited by the Berkeley computer science department, and anyway, he called Tom Hall, the chair of the computer science department, and said, and gave my name, and said, maybe you should look into this. And So yes, so Tom eventually got hold of me, not on that recruiting trip, but later on. And so Linda and I went to Toronto and eventually thought, oh, this is a great place. Actually, it was a very good budding department.
Must have been young at the time.
It was quite new, but they still had a number of people. And Tom Hall just moved there, but Kelly Gottlieb was there and Pat Hume. And in fact, before I came, Alan Borden, who is now quite well known as a complexity theorist, and also Derek Corneille was there, and he is a graph theorist, well known. So it was clearly an up and coming department. So yes, so certainly it turned out to be a very good choice.
And making the switch to computer science was a natural, seemed like a
Yeah,
natural.
that's true. But the people who recruited me were all in computer science. And actually, so my first appointment was half in math and half in computer science. And then, yes, I quickly switched to computer science, realizing the grass was greener in computer science department, yes.
So you presented the complexity of theorem proving procedures at ACM Stock in 1971, and that's the paper that introduces what we now call the theory of NP-completeness. How was your paper received at the time?
Actually was received very well. Yeah, I gave it to a large audience. I gave the talk to a large audience, and there were people there. I remember Michael Rabin was one, and he seemed quite impressed. He had been thinking along similar lines, actually. And so I got positive feedback from that paper for sure.
So can you briefly describe a little bit about what's in the paper, since it's not in the form of NP-completeness that we know
For
today?
sure, not at all. Those symbols were never uttered in my paper. So here's the story. I was interested in the complexity of theorem proving. In fact, that's the name of the paper, right? The complexity of theorem proving procedures, which doesn't sound very much like NP-completeness. And so when I submitted the paper to Stock, I actually didn't have my result there. I had a section on propositional calculus and complexity, and I had a section on predicate calculus, but I didn't have any really big results. But after they accepted my paper despite this, because the Stock was much easier to get into in those days than now. Its standards have gone way up. But then, when I started thinking about writing the final version, I had this idea of completeness, of complete problems. And of course, where did the idea come from? It came from completeness for recursively enumerable sets, and in fact, the unsatisfiable predicate calculus formulas are complete for recursively enumerable problems. And I knew that, and my advisor was very interested in that, so I credit him for giving me the idea, well, why can't we do this at a lower level for propositional formulas, and then the analog of recursively enumerable becomes non-deterministic polynomial time. And and then I proved that what I actually proved was that the valid propositional tautology, validity of a propositional tautology, which is in co-NP, it's not in NP, was complete for this class. But the reductions I put in that paper were not the many one reductions that Karp used and are used now, but they were Turing, polynomial time Turing reductions, which are much more general reductions. So I didn't have the words NP and P, that was due to Dick Karp later, and I didn't have the same reduction at a more general reduction, and I had only 3 complete problems, and of course Dick Karp later, a year later, had 21. I did have 3 in there. Of course, there was the tautologies, and subgraph isomorphism. Given two graphs is the first one, isomorphic to a subgraph of the other. And then and then of course you could also, instead of tautologies in general, you could look tautologies in disjunctive normal form. That was complete. And also, I did also have 3 DNFs, so conjunctive normal form with just 3 literals in a conjunct. That was also NP complete. So that's what I had in my paper.
And was there a conjecture in there about primality?
I mentioned other possibilities. Yes, primality testing. I said that's a candidate maybe for completeness. I should look and see whether I was doubtful, because in fact there are randomized algorithms for primes. I may have said that. I don't remember. And the other an open question was graph isomorphism, and that neither of those are thought to be NP complete now. In fact, primes aren't polytime. So yeah, I did mention those. And of course, graph isomorphism is definitely thought not to be NP complete, although no one's gotten a polytime algorithm for it.
So you mentioned Richard Karp's paper following on to yours. So how long did it take for researchers to sort of realize the significance of NP completeness?
Oh, I think it came very fast. I mean, it was obvious, and Karp's paper was very well written. He had 21 examples of NP complete problem. He cleaned up the terminology. He introduced P for polytime and then P for non-deterministic polynomial time. That was new notation, very clean. And he also introduced many one polytime reducibility, whereas I had the more general kind of Turing reducibility, polytime Turing reducibility. And all those were very clean, nice definitions. So that paper definitely caught on very rapidly.
So in the 1970s, there was an explosion of research. Were you surprised at the impact?
Yeah, I would say I hadn't quite anticipated that there were so many NP complete problems. I think there were 2 kinds of people working in this field. There were the logicians and the people who, algorithmic guy. And Karp was definitely an algorithmic guy. And my training had all been with the logicians, so I think that's my excuse for not realizing all of these examples of NP completeness. And I should say on this term, a similar example for the notion of polynomial time, of course, was independently introduced by Jack Edmonds, and about the same time as Alan Cobham wrote his paper, but they were from 2 different areas. Cobham was a logician, and Jack was an algorithms guy. And so, I mean, they're 2 different fields. And so quite independently they came up with polynomial time. But I didn't know about Jack's stuff at all until much later. Cobham was my source for polynomial time.
So the question of whether P is equal to NP is one that's intrigued and frustrated a lot of researchers. So I have to ask you, what's your opinion on the status of P versus NP?
Oh, well, that's easy. I think P not equal to NP, and I think a majority of complexity theorists believe it. And well, so here's my tune on this. First of all, we're really good at finding algorithms for things. I mean, there's a whole algorithms courses we teach as undergraduates, and all these methods of finding algorithms, and lots of examples. But for lower bounds, we aren't good at finding lower bounds. And here's my proof. If you look at the sequence of complexity classes log space, which is a subset of polynomial time, P, which is a subset of NP, non-deterministic polytime, which is a subset of polynomial space. So here we have a sequence of 3 inclusions, starting from log space and ending in polynomial time. There's an easy proof the log space is a proper subset of polynomial space just by diagonalization. Therefore, one of those intermediate three inclusions has to be proper. We can't prove any of them are proper. QED, we
But I guess even in 1967 now, you were telling us that your feeling was that P is not equal to NP.
That's right, based on, attempts. It really seemed much harder to solve NP hard problems, or NP problems in general. So yeah, that was I guess I conjectured that way back then, yes.
So not only is that problem, P versus NP, a central problem, or the central problem in theoretical computer science, with the introduction of the Millennium problems, Millennium by the Clay Foundation, the 7 problems, it sort of has been acknowledged as one of the most open problems.
I guess one of the most interesting open problem, important open problems, yes.
So were you consulted about that inclusion, or did you just?
No, I was not consulted about the inclusion, but after they decided it, they did ask me to make a write-up so I did contribute a write-up for that question, for the background.
And I guess before that, Professor Smale had a list of 21 problems, I think, and he included.
Oh, I guess he did. Yeah, indeed, that's right. He had already listed it as one of them. So definitely there's a consensus. This is an important problem.
So what about the bigger significance? I mean, it's even gets into popular culture, in The Simpsons or whatever. So how do you feel about that? How do you feel about what's the real significance of the P versus NP problem?
Well, I don't know. Yeah, you're right. It gets into, I guess many people know P and NP, and they don't understand what it is. But, well, obviously, it's an important question. And, well, for one thing, if P equals NP, it's going to rule out a lot of cryptography. It's hard to imagine how we could have any of the cryptographic protocols like RSA and so on. Public key encryption seemed to be impossible. And so that's on the one hand, it turns out P equals NP. And on the other hand, if P not equal to NP, of course you want to know more. You want to know just how hard is NP and so on. We can't help but learning a lot more about the problems. Either way, either way it goes, P equals NP or P not equal to NP, we're going to learn a lot more about computation if the problem is solved.
So right from the start of your research career, I guess what you'd call proof complexity has been a central focus. And I think, many computer scientists know about computational complexity, but maybe not so many know about proof complexity. So I'm wondering if you could describe a little bit what the concerns are and what some of the basic questions.
Well, of course, proof complexity is in the propositional form is quite related to the PNP question, because you want to know. I mean, a good aspect of proof complexity is you look at proof systems for proving tautologies, for example, and which is equivalent to proving negations are unsatisfiable, and so we have lots of standard proof systems for doing this. Now the issue there is, though, how long is the shortest proof? And can you get an upper bound on the length of the shortest proof in some proof system? And so the conjecture there is there's no polynomial upper bound, no matter what proof system, efficient proof system, under a reasonable definition of proof system, is there, could you get a polynomial upper bound on the length of every tautology? A polynomial in the length of the tautology, of course. And so we conjecture no. That's sort of like P not equal to NP conjecture. I mean, that sort of would imply P not equal to NP. so if there were such a thing, this is what I'm trying to say, if there were a proof system, efficient proof system that get polytime proofs to all tautologies, then NP would equal co-NP, meaning that the complement of any NP problem would also be an NP. And again, there's lots and lots of examples. We just don't think that's true. And so we conjecture. So this is all, proof complexity is certainly tied up with computational complexity. That's just one example.
And you mentioned Professor Wong's program for proving the propositional tautologies in Principia. And these days, both automated theorem proving or satisfiability solving in the propositional case has really become an important technology.
Absolutely, yeah, of course. And what was surprising is, yeah, there are theorem provers for, especially for sets of clauses, for propositional problems that are in conjunctive novel form that are incredibly efficient. I mean, they can find proofs or disproofs for even tens of thousands of clauses. And so that's an interesting very interesting, important subject in its own right. Of course, despite their great successes for some cases, you can always stump them by coming up with hard examples, like the pigeonhole tautologies is a good example.
So, besides the work in computational complexity, you've worked in other areas, including parallel computing and theory of programming languages. Is there a theme that goes through all this work that holds it together?
Well, it's all, I mean, certainly the parallel computing part is interesting, is certainly mainstream interesting complexity theory, because in practice now, computers have many, many processors, and you're very interested in how much time you save if you have a whole bunch of processors. And and there are conjectures, of course. Well, for some problems, you can't save much of any time. For other problems, you can save time hugely. So that's a very important and natural complexity question. So for parallel, what was the other?
The other one was theory of programming languages.
Oh yeah, well that's my contribution there was to Hoare logic.
Right, and I think I've heard that referred to as Cook's theorem, the relative completeness of Hoare's logic. And I was quite surprised when I heard that referred to as Cook's theorem.
Well, apparently it's had some effect in, I mean, that's really not my field with, programming language. It's a very important field, proving correctness of programs, of course, and Hoare had this logic, a whole method of proving correctness by putting in certain kinds of assertions here and there. You could use it to prove correctness of programs. So I succeeded that in a certain sense his logic was complete. So you can always do it if it's correct. So yeah, that was just one paper, but it seemed to have made a bit of a difference.
Despite all the advances in computing technology, and here I have 71, but now I should say 67, which is when you originally formulated the problem. The ideas about P and NP are still central questions in computer science. So I'm wondering why they have such enduring significance.
Well, I guess I tried to answer that before, right? Because they're obviously important, they're very important questions, and whichever way they resolve, we're going to learn a lot more about computation. And of course it's especially relevant to cryptographic protocols, which really would be much more difficult if it turns out P equals NP.
Apart from your research, you also have a lot of impact in terms of teaching and graduate supervision. I don't know the count now, but you've had over 30.
Yeah, I think it's 33, I think, or 33, 34 graduate students. Some of them co-supervised, I have to say. Especially later in my more recent years, I have to credit other people like Tony Patasi for being really good at helpful co-supervisors for students. So indeed, yes.
And I'm wondering how you see the how those three, teaching and supervision and research, interact with each other.
Yeah, well, there's no question that supervising graduate students interacts with research because your graduate students become co-authors in the papers. I mean, it's extremely enlightening and important to have graduate students. I'm very grateful to my graduate students, including yourself, because we have a joint paper. And there's no question that that working with graduate students is very enlightening and rewarding. And yeah, I also teach classes to undergraduates, and no, I enjoy that. And as long as I don't teach too many, because especially if I'm teaching in the areas I really like, which are complexity theory and logic. Those are my two favorite subjects. And I do enjoy teaching those courses because I think they're really neat, and I try to get the students to agree.
Well, I have to say from my personal experience that I think from the first time I walked into your office, you just treated me more as a colleague than a student. And I think it all was driven by real interest in the research questions.
Absolutely, yeah. Well, he's definitely a helpful colleague indeed.
So you're known to be an avid sailor. When did you first start sailing?
The first serious time I started sailing is when I went to Berkeley. I had tried to sail a few times. Even at Harvard, you sail, the sailing there on the river isn't too good, but so I decided not to. But when I went to Berkeley, and then you could stand up on the hill and see the San Francisco Bay opening up, harbor opening up for you, and all the boats out there really looked like fun. And I said, okay, I'm going to learn to sail. So I joined the student sailing club, UC, whatever it is, UC-wise, University of California club, but they let faculty members in, and so, but I joined, and they had a very nice teaching program on Sundays. And you see, you went to Sundays, and you get in a boat, and you had a teacher, and it was all very reasonably priced, and they would teach you how to sail. So I really took to that right away, and became a good sailor. And the other thing is, I met my wife because she was secretary. She was an undergraduate. She was secretary of the club, and so that was a great two good reasons why I learned to sail. But yes, I absolutely enjoyed it.
And you're a member of the Royal Canadian Yacht Club?
Yes, that's true. And so yeah, Linda and I are members of the Royal Canadian Yacht Club here. That was a recruiting tool by Tom Hall, by the way. When to come to Toronto, he pointed out we do have a lake here. We don't have the ocean, but we do have Lake Ontario, and they do sail. And he invited a member of the RCYC to lunch to explain how good it was. So indeed.
And you raced for a long time.
I still do.
You still do?
I still do. Yes, from the very beginning I took to sailboat racing, and I still do. Right now I sail, the club owns a fleet of called Ideal 18s, two-person keelboats that are easy to sail, but they're all alike, and we all go out and race, have races Thursday evenings and sometimes on Saturday. So I still do that, and I get a kick out of it.
So you mentioned your wife, Linda. You still live with Linda in Toronto, and for a long time, she worked at University of Toronto. Is that right?
Yeah, she worked at the admissions office at first, and then at the registrar's office at University College. And then we started having children, and after a while, we realized that it was tough. It was better that if she quit, so she eventually quit and stayed home.
And you have two sons, and I guess both of them have followed in your footsteps in their own way. I'm wondering if you can tell us a little bit more about them.
Well, Gordon is the older one, born in 1978, and he took to sailing very early. well, we encouraged him, of course, Linda and I, and in particular sailing in the Optimus dinghy, which is for children 15 under, and they have a world-class racing, it's a world-class racing boat. Optimus dinghies, they're, 8 feet long and not very big, and have one sail, and they're for children. But they have international regattas. Anyway, Gordon took to that right away and practiced and raced in the local races, and eventually he competed to represent Canada in the Optimus Worlds, and only 5 boats are allowed from each country. So he did that, and he actually did that twice, and once it was in Greece, and the second time was in Spain, and I got to go, and it was great. And then he graduated, he got his engineering degree from Queen's University, and started a little company making carbon fiber stuff. But then he really liked sailing, so he decided to try out for the Olympics, and so he worked very hard to, this is in the 49er class, is one of the Olympic class racing boats. It's a 49er, it's about 14, 18 feet long, and very hot boat, very fast. And so that was Gordon's choice, and he worked very, very hard, and eventually competed for Canada in 2 different Olympics. In 2000, in 2008, it was in China. In 2012, it was in England.
And James.
And James. James also started out sailing, but he didn't take to it quite in the same way. But he was certainly interested in computers from age 3 on, and also mathematics. So that was his thing. And so he got his undergraduate degree at University of Toronto, and in math and computer science, and then he went on to Berkeley and got his PhD in computer science. And now he's working at Google in Silicon Valley and really enjoying it.
So I have one last question. What advice do you have for young researchers who are interested in starting a career in computer science or mathematics?
You know, that's a really hard question. I guess my only comment there, as far as computer science goes, I think they need no encouragement, because right now, as you know, and I know, undergraduate institutions are being flooded with people who want to take computer science, and it's in our department, it seems more than we can handle. We have to turn them away. So somehow computer science has become an enormously interesting field, and probably with some good reason. I mean, I think the big driver now is artificial intelligence and machine learning. We're all seeing exciting things happening from that. So, and of course, it's a good field to go into, no question, but there's going to be lots of competition.
Yeah. So, I guess, I don't know, I've asked all my questions, but I don't know if there's anything else.
I think you covered it pretty well.
Good. Well, I really enjoyed talking to you.
No, really enjoyed your questions, and very nice of you to come. How much time have you taken? I don't know.
I'm not sure.
It's 2:28, so it's probably been about an hour,
Yeah.
I think. Yeah.
Well, I hope they consider that to be enough. Don't want to bore people too much.